Okay, let's talk about decision trees, and this will lead us to talking about random forests. So the basic idea behind decision trees is we're just going to create a heuristic that is going to create a nonlinear classifier or a nonlinear regressor, and we're going to do it based on recursion, which is just going to dyadically or split the domain based on axis-aligned hyperplanes. So to illustrate this, let's consider the following mock data set. So the first split that we might make is just trying to do an axis-aligned, use an axis-aligned separating hyperplane to split the data as equitably as we can into predominantly red and predominantly blue, pluses and minuses here. So we might draw a line, such a hyperplane here, which splits the reds, where we might predict the reds on the right side of that line and the blues on the left side of that line. And we would probably do better than random guess at that point. Now this is not going to give you the best performance, and it's of course because of the restrictiveness of just a single axis aligned split. But what we're going to do is now consider the right-hand side and the left-hand side as separate data, and then we'll just continue to make splits in this fashion that are axis aligned. So let's just focus on the right-hand side. We might then split this here, and now the data on the right-hand side is exactly split into red and blue. So now we might terminate the algorithm because there's unanimity of the class labels on on these two rectangles. Then we further might split it, split this left-hand side rectangle down the center. So we would choose to align it with the x-axis. And then we might further try to separate out some of these other red points from the blue points. And we may, for example, split here, or for example, split here, and then here and here, depending on what our stopping criteria would be. Eventually, if we continued with splits like this, we would be able to completely isolate points of the same color and get regions that are completely, maybe we would do it like this, something along these lines, regions where we have complete unanimity of the class labels within these rectangular regions. Now, the fear of doing this, of growing your decision tree all the way down, might be that you would overfit. So you'd typically stop the decision tree at some point based on some stopping criteria. So how can we think about this mathematically? So we can also think about this as a dyadic, as a tree, a binary tree, where each node, internal node in the tree, corresponds to a split, and then the leaf nodes correspond to one of these rectangular regions and a corresponding prediction. So for example, we have three covariates. We have covariates x1, x2, and x3. And this first initial split would be along covariate x1, which we would split at the 1.5 point. So if say x1, it's more intuitive if the left-hand side is less than or equal to. So we would start by saying, does x1, for example, is it less than or greater than 1.5? If it's less than, then we're going to think of that data point as descending down the left-hand side. And if it's greater than, we're going to think of this data point as descending down the right-hand side. Yeah, let's draw this so that we give ourselves some room here to grow the tree. Then for the data that follows this left-hand side, for the data such that the first coordinate is less than or equal to 1.5, we might further split it at x2. So let's say x2 exceeds, say, 0.2, or it's less than or equal to 0.2. Then we might further split along this decision. X2 exceeds 1.2. And then perhaps for the data on the right-hand side, where x1 exceeds 1.5, we could split along a different variable, let's say x3. So x3 could exceed, the split could be less than or equal to 0.1, x3 exceeding 0.1. And then we could continue to split, but let's just suppose that we terminate here. Then at these nodes, which we call the leaf nodes of this tree, we have a rectangular region, and y hat within this rectangular region would be some prediction based on the class labels or the observed y's within the regions. So this would be the y hats for each of these regions. And then when we go to predict, so we haven't really discussed how we would fit, we just are discussing the prediction mechanism and the decision function here. Our y hat prediction of x, it's going to be equal to the sum over our rectangles of this m going from 1 to r, where little r is the number of rectangular regions. So if you think about this, this whole area is one of these rectangular regions, for example. And it could be unbounded on some sides. So it's equal to the sum of these rectangular regions of the y hat r sub m. So the y hat for that rectangular region, the indicator of x within r sub m. Right? Where this r is just the number of these regions, which is also the number of leaf nodes. So for this tree, r is equal to 4. Right? And so the idea is that it's actually pretty easy to tell whether x lies within one of these rectangular regions, because you can just feed it through one of these decision trees and just at first check if x1 is greater than or less than 1.5, and then if it's less than, check if x2 is greater than or less than 0.2, and so on. So it's actually quite easy to do predict. You just have to effectively send this x down to a leaf node of the tree. So the big issue, of course, is in fitting, and there are two things that we need to fit. One are the rectangular regions themselves, which correspond to those splits, and the other is this y hat for each rectangular region. So how do we fit? Well, let's first talk about regression in the regression context, because it's sort of easier in that setting. So the first thing we would do is we would try splitting our data into half planes. And really there's just d times n of these possible half planes that we would consider, because if you think about it, if I decide to split along, say, the x-axis, then I really only need to try as many x splits as there are data points, because it's not going to change any of my empirical errors if I decide to make this split somewhere in between, say, two adjacent possible splits or data points projected onto this x-axis. And then I have to do this for each possible axis. So we're just going to try splitting into these half planes. And then let's denote these regions that when we make one of these splits, R1JS and R2JS, where J is the variable that we're splitting along, so the axis that we're splitting along, and S is the split itself, so it's the location. So this is equal to the x such that xj is less than or equal to S. Right? And this is x such that xj exceeds S. Right? So, so now we have these two regions for every j and s pair. And we really only need to consider n different s pairs. Now all we have to do is try every possible j and s pair. And then we have to do some sort of a minimization, turn this into a minimization problem. So how are we going to do that? Well, we're going to minimize something over a selection of j and s. That something is going to be our best estimate, our empirical risk minimizer, subject to something that's constant over those two rectangles. So what does that mean? Well, we're going to minimize over y hat 1 of the sum over xi lies within rectangle 1 of j and s of this loss of the yi and y hat I. So we can actually choose our favorite loss here. Right? So for example, square error loss would be just fine. Plus the minimum over y hat 2 of the sum of xi lying within r sub 2 of j and s of this loss yi and y hat I. So this is one possible solution, and it's pretty straightforward. If I told you that I have these two regions and your prediction must be constant within the two regions, what are you going to choose as your predictions? Well, you're just going to try to minimize the sum of losses for each of these regions. Right? So in the case of square error loss, this y hat I, this is just going to be the average of the yi's within the region. Right? In the case of square error loss. So, so that's how we actually make our predictions and how we select S and J. Now that we have this S and J, we can divide our data into two regions, and so then we get to just recurse, as we mentioned before. So we're just going to recurse these two steps, 1 and 2, on this R1 and R2. Okay. So, so this is pretty straightforward, and it's really just we're going to be doing this successive empirical risk minimization based on these dyadic splits. So it's like a greedy algorithm for minimizing empirical risk. Okay, so in classification, there's a couple of things to mention. So first of all, in classification, and this is in the multi-class setting, so we're going to go more general right away. So there's 1 up to capital K classes. Before I think I was denoting it 0 to capital K minus 1, but now there's not going to be a special class at all, so we're just going to say it's 1 to capital K. And then we can use, for example, our loss between yi and y hat I, that we can use this equaling the misclassification indicator, so the 0-1 loss. So that's something we can actually do with this. We can actually, in this example, use the 0-1 loss, which wasn't possible for example, for linear classifiers, right? But because this is a greedy algorithm, and there's only d times n possible choices of splits, we can just calculate what the misclassification rate would be for a given split, and then just choose the split that minimizes that misclassification rate. So that's one way to select our splits. But that's not the only thing that we would need to do. Now, one thing, just to think about these this loss, and how would we, for example, come up with a soft prediction for the y hat, instead of, if we have 0, 1 loss, then of course we're going to either predict it as a 1 or a 0. But in a lot of examples, we actually want to output probabilities or predicted probabilities, or something that is not a hard classification but a soft classification. So one thing that we can do is we can calculate this empirical probability for a given class within a region. And this is like a restricted, this is like a maximum likelihood estimate. So this is 1 over the number of xi's within the region. So if we have region Rm, so rectangular region, times the sum of the xi's within the region Rm of the indicator that yi is equal to k. So this is just the proportion of data points that belong to a given class k within the region. Right? And so this is going to give us some estimate of our probability of being within class k for a region. Now our y hat I, for the 0, 1 loss, y hat I, this is just going to be the argmax, or sorry, yeah, the over k of this p hat m k for xi in R sub m. So for a given xi, what's our prediction going to be? Well, that's just going to be this p hat, the class that maximizes our estimate p hat, and that's what we would get if we use the 0, 1 loss. You can check it out by plugging 0, 1 loss into problem 2. Now, there's a couple of tendencies that we see if we use 0, 1 loss. One thing is that it can often give unbalanced regions, so that it'll have this tendency to separate out smaller regions that contain just a couple of points, for favor of having a completely pure classification. So that's one thing that's sort of observed, and there's a couple of other criteria that people often prefer, that they just observe empirically don't have this behavior. There's also other information theoretic reasons to use other notions of empirical risk. And so I'll just mention them right now. So one of them is this Gini purity, called the Gini purity, and it's the sum over every pair of k and k prime, so two classes of this p hat m sub k and p hat m sub k prime. Oops, sorry. Yeah, that's right. Another way to express this is just to write it as a sum over k of p hat mk 1 minus p hat mk. That's another way to express this. And what this ends up being is a measure of how closely this region is entirely one class. You can imagine if p hat is 1 for a number, and then for a k, and then 0 for all of the others, then there's going to be one of these elements is just a 1. And that's the maximum value it can attain. So that's one thing. That's one measure that we might use for selecting our regions. So this measure then would be accumulated over regions. Another is the cross entropy. So our cross entropy for our given region is the negative sum over k of this p hat mk log p hat mk. Another information theoretic measure of how associated the region is with a given class. So that's another measure that people often use for selecting a split in classification. Now, how do you select a stopping criteria? So stopping criteria is often, there's many of these. There's some complicated pruning strategies, but I'm just going to tell you about one, which is just fix the depth of the tree. And think of the depth of the tree as your tuning parameter. So there are sort of other information theoretic reasons behind using depth of tree as a measure of complexity of the tree, but oftentimes we're going to use the depth of the tree as our tuning parameter here. So that concludes our talk about decision trees and simple decision trees. And they're very flexible methods, and it turns out that they can be successfully employed as simple learners that are used in more complicated strategies that like random forests and boosting. So.